Hello everyone, I'm Youngkook Kim. So let's start to the General Physics course 1. My name is here, Youngkook Kim, and since this is physics course in English, so my name is Youngkook Kim, and this is my office. So this is the 31st, is the first science building, and then this is second and first. So 201 is my office, and 31 means this is first science building. If you are not accustomed to the system that, well, SKKU named the office, and this is my email address. Well, you can contact me through email anytime you like. And well, office hours and so on. If you wanna talk with me or have a meeting with me, then you can email me and schedule the time. And well, I'm basically theoretical physicist. I'm specialized in studying condensed matter system. In Korean, it's 응집물질 물리 이론. You can contact me anytime. Well, so basically my door is open. Office door will be open from 3 p.m. to 5 p.m. for every Monday, so you can walk in if you like, but well, it would be better if you can email me and schedule the time first. Well, you already know this. This is the book, and this should be fixed there. You know, well, we're gonna have the meeting, so. And this is iCampus, the notice, and well, as well as this obviously you already gone to the website to watch this video, so I'm pretty sure. And important information. This is evaluation. Now we're gonna give you a evaluation. It's based on it's a 40% midterm and 40% the final term, and homework will have 10% and attendance call will make. Although we're not going to do for this class, now we're gonna give you 10% of the evaluation for your attendance, and then we will make it into the normal distribution so that the all classes, including ours and the other classes, will have the same exam. And then we normalize the scoring and compare the classes. Well, basically, I would like to give a call attendance check every class, and let's see how it will be like. So it's another important notice. Give you a final exam and midterm. General physics class will have the same midterm and final terms, and we will give you a notification by the time we fix the plan, the how and when we're going to give you exams. But before, what we have done is we give you one problem from past year's midterms, and another one from the example in the textbook. And it would be better if you can solve all the previous given problems and then examples. Okay. Well, this is contents that we're going to cover for this semester. Yeah, there are many. So the first, we're gonna learn about the motion and the motion of a particle, and we will describe and understand the motion of a particle in terms of force. And then, well, we will give a different perspective or different way of understanding the same phenomena in terms of energy. So we can understand the motion of the particle or particles, multiple particles, in terms of force and as well as in terms of energy. And then we're going to see how they are related. And what we are interested in energy is the energy is conserved. So there are many conserved quantities in universe, and energy is one of them. And then that gives it, conservation gives very important then an insight into the motion of particles as well as the physical phenomena. Then we'll shift it to the momentum and rotation and angular momentum. Pretty much we'll extend this linear motion of the particle into the rotational motion of the particle. And then now we'll give you the meter term. That's just a plan. Plan can change. And after the meter term, we're gonna learn about the gravity and the fluid dynamics and oscillation of a wave and waves and then thermodynamics. Then you're gonna take the final exam. Again, this is just our plan, and we know that just listening and watching a video or just listening what professor teaches you will be not informative, helpful for solving problems and the good record out of the exams. Instead, I strongly recommend you to teach yourself by solving many problems. So listening to recording wouldn't teach you to play, and listening to lectures wouldn't teach you either. So that tell you that write down your equations and solve as many problem. All right, and as I already am doing now, the lecture will be based on English. I'm open always the questions. You can stop anytime you like. There is no stupid questions. Ask a question. So if you stop me and ask any questions, so you're always welcome to ask a question. I would like to give you homework for every chapter. This is a physics course for both scientists and engineering, and we're going to start with the introduction to the physics and measurements. Let me ask first this question: what is physics? So physics is from ancient Greek word, means knowledge of nature. This is one of the natural science, of course you know, and is dealing with motion of matter, particles, or fluid, or waves, or and then they deal with the dynamics and motion of these physical objects, and its motion and behavior through space and time will be the subject of our physics, along with related concepts such as energy and force. One of the most fundamental scientific disciplines. Then the main goal of physics is to understand how the universe behaves. So universe include everything. So it's underlying principles that we are so much interested in as a physicist to understand all the phenomena that happens in universe. Well, there is common misunderstanding on the idea of physics. Physics is a science, so matter is not only including real matters, but matters sometimes include how people behave or anything that you can think, or even traffic and so on. Well, that's so the subject that physicists like to answer, but problems will deal with the matters that can be understood in terms of fundamental principles, and which is a reproducible, the principle that governs the universe, what physics wants to study. Well, and then a common myth about the physics is physics of why. So it's more like why there is universe. It's not sort of the question that the physicists like to answer. It's more like philosophists or the theologists want to answer. The reason something that we don't know. And well, but instead of physicists like to answer the question about how, not why. How materials moving around, or how the universe first started, instead of why the universe started it in the beginning. Well, that's pretty much a different questions. So once you know the principle of the universe, and then we want to take advantage of the principle to answer how the universe works. Okay. The bottom line I would like to deliver is the physics is about more like how, not why. If someone asks you why did you lose weight? You can say, well, there is a lightweight boxing tournament. So that could be a good answer, but this is not scientific. You can instead ask, how did you lose weight? Well, it worked out 3 hours per day. Well, then that's more like scientific because, well, if you do that the same, then that is reproducible. You can also lose weight. This is sort of a unique science in the sense that, well, there is a clear cut between theory and experiments. It's not really hard to find a physicist who do both theory and experiment. Physicists are specialized either theory or experiments. Physicists usually are divided into two exclusively. The dream of theorists, I guess, is to propose a theory that has their own name. And then that theory is developed to explain phenomena which is seen from experiment. That's how it works. And the reason why we want to know about the theory and the principle is that once we know the principle, that can also apply to other problems or different problems. Apparent problem looks different. What physicists like to understand is that there is a common principle that we can learn from these two experiments or the phenomena. Then, well, once we capture that principle, so fundamental, it governs the law, we can apply them to a new problem. More importantly, predict the phenomena. Good theory has a good predicting power. And of course, the physics is based on the mathematics. While you can do logic in terms of a computer program can be used to physics, but the underlying language is mathematics. It's always good to know mathematics to be good at physics. Well, there is a distinction between classical and modern physics. When people call the classical physics belonging to the physics that is developed 19th year. So, well, you might wonder why it's supposed to be like that. So the reason why is that, well, the distinction is not just the time, but the contents, but the theory that is developed by the time is not the 20th century started. So, which is made of relativity and quantum mechanics. So, by the time of the end of the 19th century, the modern physics started. So, and then the physics still is a subject of study these days. So that's why we call it modern physics. But, well, the bottom line is, well, the physics that is developed up to the end of the 19th century is a classical one. It still works for a certain range of phenomena, but beyond that, classical physics usually don't work. And the new theory, modern physics, includes the relativity and quantum mechanics. Okay, when is the time that distinguishes the classical physics and the modern physics is end of the 19th centuries. Then, well, all the physics that you will learn, well, the classical physics, and Galileo in 1600 years, and Newton that you know, and Maxwell's still they are all the classical physics. Einstein's relativity and many geniuses, quantum mechanics, Bohr or Heisenberg, or belonging to the modern physicists. You will have a chance to learn a little bit about the modern physics, but most of the time, the subject of this general physics is classical physics. Okay, so well, the physical phenomena is measured, or in terms of experiment, the object that measured by the experiment is quantities, and then the quantities could be divided into different levels, but the fundamental one listed here, which includes length, mass, time, and temperature, and electric current, luminous luminous intensity and the amount of substance and so on. So these quantities could be measured in different units, but as in standard unit, well, we agree to use this. By that, by we, I mean the old physicists or all the scientists would like to use is a standard unit, but it's not always. We use that unit because that's clear to understand the physical phenomena. So length is described in terms of matter. So this could be a few feet, but well, you do say that this is 1 meter, is much easier, and while the mass is kilogram and time is a second, because this determines, the unit determines the scale that we are dealing with the problems or the phenomena. So we are dealing with the matter that can be measured in terms of matter. So the matter is a good unit to measure. Let's say like my height or your height. Your height is 1 point something. That's all measured in matter. Then you have sense how tall he or how short he is, she is, and so on. Also, the kilogram is, we have a good sense of the kilogram. Well, if I ask you to lift, let's say 100 kilogram, you will feel like, it's impossible. So the kilogram tells you how much the sense of the weight and the second also as well. So pretty much this unit works very well in everyday life and temperature and so on. So that's we call it the standard unit. And then in terms of these units, all the physical quantities described, like force, energy, displacement, velocity, acceleration, which I'm going to explain later. But pretty much this slide tells you that you have to be accustomed with the unit. Right, here's the examples of unit. This is a little bit tiny. I'm not sure if you can see this, so let's increase it. So, that's interesting information. So let's kill that one. I shifted that one, and this is distance from the Earth to the most remote quasar. This is a celestial body. This is 1.4 times 10 to the 26 meter, which is, I don't even have the feeling of the length, but pretty much that's long. On the other hand, the diameter of the proton is around 10 to the minus 15 meter. That's pretty small and tiny. So we have many different scales that can be described in terms of unit matter. Okay. Look more if you like, but let's go on. Well, mass is based on specific cylinder. So there is a specific 특정한 that cylinder that has internationally kept in the as a standard kilogram. So 1 kilogram is based on a standard cylinder, and then measured relatively from based on this 1 kilogram of mass. And I see that visual universe, the universe that you can see is belonging to of course you cannot see all the universe. So the distinction between the visual universe and dark universe is technical, and it's not just the way the bare eye cannot see whole the universe around the 10 to the 52 kilogram. Anyway, so that it's pretty much a large number, large mass. An electron has 9.11 to the 10 to the minus 31 kilogram in terms of kilogram. It's pretty small. So it's two extremes. And time, it's we are using seconds, so it's defined in terms of visualization of radiation from cesium atom. So cesium atom radiate photon in certain time, and that time is not changing, not affected by the environment. It only depends on the cesium. So wherever you are, if you have a cesium atom, and then the radiation oscillation time is always the same. So that's good standard. So based on that standard time, you can measure relatively the other times. So the universe has a 4 times 10 to the 17th second in terms of second. That's very long. And at the other extreme, the time interval for light to cross the proton is around 10 to the minus 24. Well, sorry, this is just jumped to the previous slide or two, and you see that the unit could be very large and sometimes very small. So I don't want to say always the fraction of the unit, like 10 to the minus 12 or 10 to the minus 24, 10 to the minus 9. Well, instead of using it, we would have a better name, such as nano or yocto and so on. So instead of saying 10 to the minus 3 meter, it would be better to say 1 millimeter. And as well as for the 10 to the 3 meter, we would be better to say 1 kilometer. I'm pretty sure that you are all accustomed with these units, millimeter and kilometer, but it will be not always the true when the number grows infinitely large or number showing dwindles infinitely small. So for the case of 10 to the minus 12, which has a also name prefix yocto, and an abbreviation for that yocto is Y, and then japto or atto. I'm sure that you start to hear about the femto and pico, and nano is more popular these days, and micro, and millimeter, centimeter, decimeter, kilometer. And what's the 10 to the 6, which has an abbreviation of M, that's mega. And then I know the next unit, so prefix is giga, and tera, pepta, ecta, jetta, and iota. And these are all. So the distinction is made by the lowercase and the uppercase between two prefixes that starts from both Y. Okay, so be aware of it. And we say that there are basic quantities, and then that's length, mass, and time. That's good quantities to describe the dynamics of a particle, especially for our purpose. So dimension has their specific meaning. So that's a physical quantity that is clear distinction, that has clear distinction with another quantity. So you never become a length when it starts from time and so on. And when people represent this with this bracket notification with L, then it is representing lengths instead of using full word. People usually sometimes use abbreviation of the length by putting into the square brackets. Same happens for mass and time. And quantities dimensions is represented by power of the letter. So once it has 2, that means area, and 3 becomes volume, and so on. Let's skip this part. And what you can do, you can quickly analyze the dimension and see your equation is correct or not. So what I mean by that, well, you can drive your equation and end up having this form. Then what you have to do is to check whether your left hand side and right hand side have the same dimensions. That's sort of dimensional based, can be done in terms of dimensional analysis. So this is sort of a technique to check correctness of an equation. Once you drive some equation and found that both sides are in same dimensions, then that's one safety check. Okay, and then, well, quantities can be added or subtracted only if they have the same dimension. So, well, if you add something, then you have to add something that has the same dimension with the already written quantity here. And on the left hand side or right hand side, both sides of the equation must have the same dimension. So that's something that you have to check. And this is when people use this bracket, square bracket, and that represents the dimension of the quantity that is inside of the square bracket. So whatever written in here is, if it is length, then this x is a quantity that is in length dimension. And the right hand side, well, this is acceleration, and acceleration is defined such that it has the unit that L over t squared, and multiplying the t squared, then it cancels the length, time on the denominator and the numerator. So you end up having the same unit with the left hand side, so it's good to go. Well, one good check. The equation is dimensionally should be correct, and then there is no dimension for the constant. So the 1/2 doesn't have the is constant, means that this 1/2 and then 1/2 doesn't have dimension. Well, to represent the quantities that I described the previous slide, is based on symbols. So there are favorable symbols in physics. So the time usually is represented by symbol t, and x, y, g, and r, d, h are favorite symbols for length. So that because the x, y, g tells you the dimension, x dimension, y dimension, g dimension, and r usually mean radius, and d means distance, and then h means height. They are all length scale. So that's the reason why people are preferable to use these symbols. So here's the very important technique, which is order of magnitude. So you have a good sense of order of magnitude, then, well, that gives you some insight. So let's say, well, this gives you an approximation using just the approximation using a power of tens determined as follow. So express the number in scientific notation. So scientific notation means that, well, you have a significant of number, let's say 3.5. Well, you have two digits that are significant number, important number, and then multiply with the 10th of power, let's say 5. So that's the scientific notation of number, let's say. And then, well, the approximation can be done in terms of the symbol, which means is on the order of. So, for example, this number 0.0086 meter is on the order of 10 to the minus 2 meter, and so on, and 0.0021 meter is order of 10 to the minus 3 meter. So is around this 1, 2, 3 order, minus 3 order, and so on, and 720 meter is around 10 to the 3 meters. So it's similar to or on order of 10 to the 3 meter. So the reason why we do that is to estimate the quantities. Let's say, well, if you are asked to ask the number of atoms in a solid, and then order of estimation is a good technique to solve answer this question. So, well, the thing that you have to account is the number of atoms in a. It's easier way to do that is to do. It's not the only way, but easier way to estimate the number of atom is estimation of the number of atom in a, is to start with something that you have a good sense of. So you might have a good sense of the number of atoms in 1 centimeter cube in terms of the diameter of an atom. So if you if you know the one atom usually have a diameter that is around 10 to the minus 10 meter, that's just order. The specific number is not important. And then assuming that the atom in a unit cell are sphere, then you might think that one single atom will have around 10 to the minus 30 cube meter, which can be estimated in terms of this volume quantity. Then once you know a single atom volume, then just divide it with divided the 1 centimeter cube with the single atom volume, then that will give you a number that belongs to 1 centimeter solid. Okay, and then well, you end up having this sort of familiar number, which is 10 to the 24 atoms. So again, the specific digit doesn't matter. What is important is this order of magnitude, and this is similar to the Avogadro number, which is 10 to the minus 24, and that gives the connection between the macroscopic and microscopic world. So if you are asked the microscopic quantity that in the macroscopic large scale system. So microscopic system is a quantum mechanical and system that you never see in your bare eye, and that's a single atom level of scale, and macroscopic is something that you can see in your bare eye, and these two connection, atom level to the object that you can see, is always connected by the Avogadro number. So if you are asked the question how many water molecules in a cup, then that's around the Avogadro number. The specific number doesn't matter, but the connection between them will be made in terms of the scale of the order of Avogadro number, which is around 10 to the 23. And also, this is again an example of order estimation. So if you are asked what's the number of breaths in your lifetime, so well, it depends on people and depends on the situation, but you can estimate the number of breaths, and the answer, the specific answer doesn't matter. What is important is the scale of the number. Okay, and usually when you have a job interview and from a company, and then well, the interviewer sometimes asks this sort of questions. So, well, the reason why they are asked is called Fermi estimation, and or the reason why they ask this type of question, that well, is to see how you reach to how you derive the answer instead of a real answer. Okay, so again, that shows you how you reason the problem, how you solve the problems, and then the way you solve the problem will be the same with the general. So the way you solve general problems. So that pretty much teaches about you. So that's why, well, job interviewers sometimes ask this sort of questions. And physicists, if you are the goal of the physics is not just the knowledge, but the way of thinking, and will be very helpful once if you study hard, not just the specific knowledge that physics is trying to teach you, but the way they reason, the way they solve is far more important. Just like this. So the key, the good idea is to count the number of breaths in a minute, which you can do immediately, and then count the how many years lifetime would made of how many minutes corresponding to approximately to the 70-year lifetime, and that's the 4 times 10 to the 7 minutes, and if you counted the 10 breaths, let's say, in a minute, then the lifetime breath corresponds to the 10 to the 4 times 10 to the 8 breath. But the specific number 4 doesn't matter, but more important is 10 to the 8, the scale of the number, and which tells you your reasoning is sound or not, depending on the scale of the order of magnitude. Okay, that's the end of the chapter 1. I will continue in the next. Okay, let's start the chapter 2. So chapter 2 is about the motion in 1 dimension. So let me first give you this an article. It's about the crash that happened in sometime in United States, and this news article goes like this: passengers told Stefan Nielsen of YNYC, whatever that is, the train approached the station at full speed. So, people use the concept of the physical quantity in everyday life that's shown here. And before slamming into the barrier at the end of the track, with the impact throwing riders out onto the floor. And witness Mark Cardona says it took him about 3 seconds to realize what happened. Well, it's interesting that this one specify the second precisely. That's interesting. As the roof started to collapse, well, that's scary. And he says there had been no warning before the train suddenly smashed into the flap again. It was going full force. Well, yeah. If you know, well, that sounds non-scientific. Well, if you done this course, please don't do this sort of misunderstanding and so on. So yeah, well, the everyday life, we use certain concept that is defined in physics, but the definition has a slightly different in everyday life, the way people use in everyday life. So it's the kinetics is about the motion, and then like the train that is crashed. So to describe the motion, and understand the motion, we should define some physical quantities. Okay, so the kinetics is about the description of motion, while ignoring the external agents that might have caused it or modified the motion. So you just deal with the description of the motion. For now, for simplicity and easiness, we'll only consider the 1 dimension, which can be easily extended to the other dimensions. So, well, let me first ask what dimension means. What is dimension? Well, you already know 차원. So you always in everyday life use term dimension, but once I asked what the dimension means, then it's hard to answer. I know. So the dimension, and so since you already know that we are living in the 3 dimension, are we living in the 3 dimension or 4 dimensions? It depends on we define the dimension with, sometimes people call 1 plus 3, which means we have a time dimension and 3 spatial dimensions. So let's see. Well, dimension is defined this way in Wikipedia again. This is mathematical space is defined as the minimum number of coordinates. Well, so in order to describe independent events, independent dynamics of system, you need to define coordinates, and then independent number of coordinates is number of dimensions according to the Wikipedia. Okay, so it means that we only deal with the one-dimensional problems because it only include one variables and along that describe the distance from one point to the other along a line, not like a circular motion or in 3 dimensions or 2 dimensions. So one-dimensional motion is simple because it is described in terms of a single variable. Okay. And then we're gonna treat the object as just particle, and this is the flow of the concept. We're gonna end up introducing this energy concept of energy, but starting from the motion. So the motion, in order to understand the motion, we'll define displacement, velocity, and acceleration, and I will understand this motion in terms of force, and then extended the idea of force into energy and see how these two different concepts will coincide. It gives the same description of the motion, the particle in motion. Okay, so the motion is has a characteristic name which distinguishes the characteristic property of motion, which is translational, rotational, vibrational. Translational means just one-dimensional motion, and rotation means rotating, and vibration is periodic motion, like a pendulum. Okay, and position is a scalar concept, so you can have just a number to describe this position. Let's say once this car is moving from A to B, then after some time it goes back to the C and D, E, F. And so in the coordinate, in terms of the number that car is positioning, which I will label X, it starts from around this point and then go to the B point and C, D, E, F, and so on. So the position tells you, well, the number. So if you are asked what's the position of the car at time C, which is 20 seconds, then you have to read of this number, 40. That's what it means by position. And unlike the position, we introduce a sort of a factor quantity, that is displacement. So the displacement is difference between two positions. The change in positions, where we use this delta notation. Delta notation always defined from final from minus initial. So if it was x, that x means the x final minus x initial. So delta x is pretty much a vector which has a direction that can be represented by the sign of the quantity. So the plus sign means and has different meaning from the minus sign. So it could be positive or negative. In the sense, this is the positive or negative, and in this sense, this quantity is a vector. Different than that's different from the position or the distance. So if this example has a clear distinction between displacement and path or the distance. So if a basketball player is started from this position, and after 2 hours of playing, if it end up having this position, then the displacement is 0 after long that efforts. But the distance is somewhat different. The distance that this player is traveling through 2 hours of basketball playing is just collecting all the infinitesimal displacement and absolute value of that, then it collects a distance. So it's quite different from the displacement. So the displacement is a vector. It just counts the initial and final position, and their difference is just the either positive or negative number. That's the displacement. But the usual concept of this distance is the collection of infinitesimal displacement, that is absolute value of distance displacement. So the distance is different from displacement. You should distinguish these. And then we want to know how fast people moving around, all the objects are moving in terms of the velocity. And it's velocity is again one of the factor that's defined by the difference from the final position to the initial position, and then divided by the time that it took to travel from initial to final. Again, since this final minus initial means that this is displacement divided by the time that took to travel from here initial final is the velocity. And the dimension is length divided by the time, and in SI unit this is meter per sec. And the position, if you draw the position is in the position time graph, the slope is corresponding to the velocity. And then here's a more scalar concept. So this is just average speed. So while instead of divided the displacement divided the distance with time, then since the distance is scalar, the quantity that is calculated by dividing time is also scalar, and so it's different than this velocity. Okay, let's solve this example. So calculating the average velocity and the speed. So you should distinguish between the velocity and the speed. The velocity is defined by the average distance displacement, but the speed is defined by the average distance. So in order to answer calculate the velocity, you should calculate the displacement first from A to F. So find the displacement velocity from A to F. So starting A to here, you just subtract it from the final position from by the initial position, which is xf minus xa, which corresponds to the minus 53 meter and minus 30 meter, which is minus 38 meter. So the average displacement is minus 83 meter, and divided with the 50 seconds, that will give you the average velocity. But unlike the velocity, the average speed is corresponding to all the distance that this car traveled from A to F. It's not just the final difference; it collects all the distances. So you need to add this distance as well as this distance. So that corresponds to the 127 meter, and it doesn't have the sign because it's a scalar quantity, and the number is 2.5 meter per sec. So the concept of the velocity and distance are different in the sense that the velocity is a vector and speed is scalar. And another example, a jogger runs in a straight line. Straight line tells you our problem is one-dimensional, and with an average velocity of magnitude 5.00 meter per sec for 4.00 meter, and then with an average velocity of magnitude of 4.00 meter per sec and for 3.00 meter. So the question is, what is the magnitude of the final displacement from her initial position? So since a problem gave you the average velocity, you can invert the formula to get the initial and final position. So this average is around 5.00 meter per sec, and it took 4 minutes, magnitude 4 meter per sec, and for 3 minutes. So the position from the first 5 meter per sec average velocity is at 1.20 times 10 to the 3 meter, and the next 3.00 that is done by for 3 minutes is corresponding to that value. So these are two distances, and the next question is, what is the magnitude of her average velocity during the entire time interval of 7.00 meter? So this asks magnitude of her average velocity. So you need to divide the entire total distance by the time it took. Okay. Unlike the average velocity, here's a sort of new concept, which is instantaneous velocity, 순간속도 in Korean. The limit of the average velocity, this is the limit of average velocity, limit is to the 0, so it's pretty much the derivative in time. So I think, well, that concept is very genius. So, well, what Newton invented the idea of calculus. So what he did is he introduced this limitation so that this value, the velocity, become a function of time at one point. That's a genius part of the invention, mathematics, calculus. Okay. Well, in graph, the instantaneous velocity corresponds to the slope at a point. So, well, if you are asked to calculate the instantaneous velocity, you should calculate the slope at the point. So, well, the average velocity is a two function over time, but you're doing the limitation. You bring all the way to the initial point, or you bring all the way to the final point, and it becomes the function of time at one point, and then you can evaluate it as a function of time. And average acceleration is defined by the same way with define the instantaneous velocity, except that we do that with the velocity itself. So when in terms of average velocity, you should differentiate. We should subtract the two finite time interval velocity difference and divide it with the time. But we can bring this time to the infinitesimally to the other time and define a quantity that depends on a single time point, that is instantaneous acceleration. It's a first derivative for velocity, or since the velocity is the instantaneous velocity is the first derivative of displacement, so the acceleration is the second derivative of point. It's a displacement. So in graph, you can read off acceleration. So the first way to read the acceleration is from the values t and time graph. So if you are given this curve and to estimate ask the acceleration at one point, what you have to do, you have to just calculate the slope of the graph at the point. Okay, that gives you an acceleration at the point. And don't forget that only applies when this graph is velocity time graph. And well, in terms of acceleration, you see that this slope is maximum here, so the slope is growing all the way to that point and then start to get smaller and smaller, and then slope becomes eventually 0, and here become negative. So you can read off the slope and redraw in acceleration time graph, then that will look like this. So here it becomes the maximum number, which means that maximum slope in the velocity time graph, and it becomes 0 when the slope is completely flat. So graphically, you can start from the displacement time graph and then bring it all the way to the acceleration and time graph. So, well, again, your velocity can be calculated as a slope at a given point, slope here, like this, and see that the slope becomes 0 and start to become negative after this time. So that can be written like this. And then again, based on this curve, you can read the acceleration. From here to here, the acceleration becomes identical, and then it starts to become 0. So it has a positive number, some positive number that is corresponding to this point, and then become 0, and negative all the way to the time e here, and then suddenly become the positive number, and so on. So you can, well, have a sense of acceleration from time position graph. So example, so the velocity of a particle moving along the x-axis varies according to the expression. So you were given expression that is relation between velocity and time, and where the velocity is in meters per second and the t is in seconds. So good. So the question is to find the average acceleration in time interval t equals to 0 and t equals to 2.0 second. So what you have to do, you have to go all the way back to the definition of the quantity. So whenever you ask the question, you start with the definition. So definition means that, well, you should calculate the velocity at that 2 points. So from this equation, so the initial point can be done by putting the time a, which is 0, is corresponding to this number, and then at p equals to 0, that becomes the where is it? I don't think I have it. So 2.0 means that 2 times 2. So 40 minus 5 times 2.0 square gives you 40 minus 20 meter per sec plus VB. So which is a V final. So 20 meter per sec minus 40 meter per sec, which took for 2 seconds, 0 second minus 0.0 second will give you minus 10 to the meter per sec square. That's the answer. Okay. All right. Next question is this: determine the acceleration at t equals to 0. Well, you can do that based on the definition, but if you know the limitation, you can just use the formula v xt was given as 40 minus 5t squared. Then the acceleration is nothing but just along the x direction. It's nothing but just xt derivative, first the derivative, which is 0 minus 10t, and xt equals to 2.0 is minus 10 to the 2.0 meter per second. Kinetics of one-dimensional particles are governed by these kinematics equations, 5 equations, and for a constant acceleration, which is of our interest, we will only solve the problems for this chapter that has only constant acceleration. When acceleration is constant, there are 5 equations that you can utilize to solve the problems. That some of these equations just with definition, such as this one. Well, the final velocity can be obtained in terms of acceleration. That's again, well, reformulation of the definition for the acceleration and so on. So every equation here is just a reformulation of the definition. Well, so using this equation, you can calculate the variables, which is the final velocity and initial velocity, acceleration, and then the time, and as well as the position change from initial to final. And when acceleration is 0, these 5 equations fall into a simpler equation here. So the final velocity is maintained as an initial velocity throughout the whole time. So equation becomes much simpler. But for the final velocity without changing any velocity with 0 acceleration will be obtained in terms of just the adding the additional velocity times t, which gives you more final velocity. Well, if you take a closer look at the problems and solve many problems, you will find that, well, all the problems fall into finding 2 unknown variables from 3 given values of variables. So you have to find out 5 variables, which is initial velocity, final velocity, and constant acceleration, and the displacement and time taken to travel from initial position to final position. So these 5 variables are variables that you have to find out eventually. So the problem looks complex, but it falls into the problem is to solve two variables out of these 5 and use the equation that is listed here to find the other variables. The reason why I'm saying that out of 5 you only have to find 2 unknowns and 3 should be given is that although there are 5 equations, only 2 equations are independent. In fact, you can derive the other 3 equations using these 2 equations. So the number of unknown variables that can be newly obtained from the physics equations is just 2. Well, so I strongly recommend to memorize this equation and this equation as well as this equation. The reason why you have to memorize the third equation, although this equation has the same amount of information with the equation 1 and equation 3, this is easier to solve the problem. Sometimes when you are given with the variable that is displacement and an acceleration, it's easier to solve problems using this equation than the other 2 equations. So for the convenience of solving problems, it is better to remember these 3 equations. Let's take a look at an example. So suppose a jet lands on an aircraft carrier at a speed of 63 meters per second. So the aircraft carrier moves at a speed of 63 meters per second and jet lands on that carrier. What is its acceleration if it stops in 2.0 second due to the arresting cable that snags the jet and bring it to a stop. So the acceleration, the final velocity is 0 because it rests, and due to the snagging the cable, and then initially it was a 63 meter per sec. So the final minus initial, and then the time taken for is 2 seconds, gives you an acceleration, which is this number. So while analyzing this problem, this is constant acceleration problem. So you will only see a constant acceleration problem here in this chapter and throughout the chapter for the one-dimensional motion of particle. And then, so see that the jet lands on an aircraft carrier, and then the speed was 63 meter per sec of the jet aircraft. So the aircraft jet has an initial velocity. So this initial velocity out of 5, I said that there are 5 variables, which is initial velocity, final velocity, and time taken, and acceleration and displacement. So initial velocity is given, and what is the acceleration after it stops? So which means that after stop, the final velocity becomes 0. So throughout the problem, these 2 variables are given, and then in addition, there is additional information that is stopping 2 seconds. So it took 2 seconds to stop. So 3 variables are given. As I said, the problem is always has this structure. So out of 5, 3 are given and 2 are asked to answer. So the first question was asking this acceleration, which is solved here. And the second question is, of course, the other unknown variable. So if the jet touches down at a position x initial equals 0, what is the final position? So it kept asking this. It asked this question. So again, once you notice that although you have many different problems encountered, still all the problem can be broken down into the question asking 2 unknown and 3 from 3 given variable will give you a relief on solving problem and encourage you to attack problems. Okay, we'll skip that example, and now so one example is more like a physical example of constant acceleration is freely falling object without dragging force, without the resistivity. So the freely falling object is an object moving freely under the influence of gravity alone. So resistance is neglected for now. So object feels the same acceleration, which is counterintuitive, but it's true. So so all the object, no matter if it is a feather or an apple, these objects feel the same acceleration, constant acceleration from the Earth, which is 9.80 meter per second squared downward. So the freely falling object is just dropped and then thrown upward and then downward. But in any case, acceleration is constant. As I promised, that all the problems should be a constant acceleration problem. And then the initial condition could be different. If it's dropped from the rest, then the initial velocity is given as 0, and thrown upward is minus velocity with respect to the gravity direction. And then thrown upward means that in the other way. So the downward means that the sign is the same with the acceleration direction and upward on the other way around. So anyway, all object feel the same acceleration. This is one example of constant acceleration. So let's take a look at this movie from YouTube. Let's see. Oops, sorry. Well,
this is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's got an eccentric construction.
And they
The light one, and drop them at the same time to see which fell fastest.
In the present of course you see the is heavier than apple. So it's a bowling ball.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance.
So the story goes different. It's counterintuitively when all the air is sucked out of the chamber.
6.
So this guy
5,
cannot
4.
be inside anymore.
Cameras on.
And
2.
then drop
1.
the same
Release.
object and see that both bowling ball and feather falls with the same speed and acceleration, which is very exciting. So coming back to our problem, our object, the free falling object is characterized by the same acceleration, which is g, and minus sign here means that it's downward, and there could be 3 cases depending on the initial velocity. For the free falling case, without the initial velocity, it starts from the initial velocity 0, but once the initial velocity was negative, it's thrown downward. So, and then if the initial velocity is opposite and then positive, then it goes a little bit upward, then go back to the downward due to the gravity. So in terms of equation again, the initial velocity is just as different sign or 0. Let's solve this example before we stop the class. Well, for us, a stone is thrown from the top of the building is given as initial velocity 20.0 meter per sec. So it is upward. That tells me that, well, this problem gives me an initial velocity which is 20.0 and positive. And also, since the ball is freely falling, although without saying it, although the problem doesn't say that this is a constant acceleration problem, and the out of 5 variables the acceleration is given, so already 2 variables are given, and then 1 more should be given more. And the stone is launched 20.0 meter above the ground, so that tells me again the initial position. And then the question is just the edge of the roof, it's way down. So the stone just missed the edge of so that means that this stone is thrown exactly the upward, and without traveling lateral direction, perpendicular direction, it just go vertically down. That's what it means by the stone just missed the edge of the roof on its way down. Then the question is using the initial value time is 0, so that here we go. Here is a variable given as the time. No, it's not the variable. This is initial condition, so we can use the time as just the variable. As the time leaves the thrower's hands at the position A, determine the time at which the stone reaches this maximum height. So, well, although it doesn't say, it asks a question about the maximum height, which means that at the maximum, what happens is that the velocity becomes 0. So well, you are given with 3 variables, and then of course the question will be to answer the other 2 variables. So initial velocity was given, and time is asked, and acceleration is given, and final velocity is given. So time is solved that way. So the acceleration is given, final velocity is given, initial velocity is given as minus 20 meters per sec, and so on. So the 20.4 seconds is the time that takes to reach to the height, maximum height. Then find the maximum height of the stone. So that's the asking the traveling distance. So that's the last variable that is not that needs to be solved. It can be solved easily using this equation, and I got the answer 20.4 meter. Okay, finally, determines the velocity of the stone when it returns to the height from which it was thrown. So again, it gave you the initial final position, which is 0, and since you are given with the initial velocity, the final velocity will be just the same with the hypothesis intuitively, but also it can be solved from the equation like this. And finally, this is a final problem. So find the velocity and the position of the stone at 5 equals to the time equals to 5.00 second. So the velocity and the position, these are 2 variables, and the time is given, acceleration is given, initial velocity is given, 3 variables are given, and then these are 2 variables. So you can solve it using this equation and this equation. So everything's easy. So this is the end of the chapter 2. So the what is important thing that I want to tell you is that initial velocity, and final velocity, acceleration, and time and distance are 5 variables that you want to know or problem asked, but they give out of 5 they give 3, and you need to calculate only 2 then using the problem. And the condition is not explicitly said, but sometimes it's implicit, but you have to get that information out of the implicit information. Okay, but all the problem is corresponding to finding 2 out of 3.